Como siempre, bienvenidos a una nueva edición de Física en IEI High School, empezando con la invitación de ver nuestro anterior video sobre Physical Quantities. Our study of physics opens with kinematics, the study of motion without considering its causes. Objects are in motion everywhere you look. Everything from a tennis game to a space probe flyby of the planet Neptune involves motion. When you're resting, your heart moves blood through your veins. Even in inanimate objects, atoms are always moving. How do you know something is moving? The location of an object at any particular time is its position. More precisely, you need to specify its position relative to a convenient reference frame. Earth is often used as a reference frame, and we often describe the position of an object as it relates to stationary objects in that reference frame. For example, a rocket launch would be described in terms of the position of the rocket with respect to Earth as a whole, while a professor's position could be described in terms of where she is in relation to the nearby whiteboard. In other cases, we use reference frames that are not stationary, but are in motion relative to Earth. To describe the position of a person in an airplane, for example, we use the airplane, not Earth, as a reference frame. Thus, you can only know how fast and in what direction an object's position is changing against a background of something else that is either not moving or moving with a known speed and direction. The reference frame is the coordinate system from which the positions of objects are described. So, what is the difference between distance and displacement? As we study the motion of objects, we must first be able to describe the object's position. Before your parents drive you to school, the car is sitting in your driveway. Your driveway is the starting position for the car. When you reach your high school, the car has changed position. Now, its new position is your school. Physicists use variables to represent terms. We will use d to represent the car's position. We will use a subscript to differentiate between the initial position, d sub 0, and the final position, d sub f. Now imagine driving from your house to a friend's house located several kilometers away. How far would you drive? The distance an object moves is the length of the path between its initial position and its final position. The distance you drive to your friend's house depends on your path. Distance is different from the length of a straight line between two points. The distance you drive to your friend's house is probably longer than the straight line between the two houses. We often want to be more precise when we talk about position. The description of an object's motion often includes more than just the distance it moves. For instance, if it is a 5-kilometer drive to your school, the distance traveled is 5 kilometers. After dropping you off at the school and driving back home, your parent will have traveled a total distance of 10 kilometers. The car and your parent will end up in the same starting position in space. The net change in position of an object is its displacement, or delta d. The Greek letter delta d means change in. The total distance that your car travels is 10 kilometers, but the total displacement is 0. If you are describing only your drive to school, then the distance traveled and the displacement are the same, 5 kilometers. When you are describing the entire round trip, distance and displacement are different. When you describe distance, you only include the magnitude, the size or amount of the distance traveled. However, when you describe the displacement, you take into account both the magnitude of the change in position and the direction of movement. In our previous example, the car travels a total of 10 kilometers, but it drives 5 of those kilometers forward toward school and 5 of those kilometers back in the opposite direction. If we ascribe the forward direction a positive and the opposite direction a negative, then the two quantities will cancel each other out when added together. A quantity such as distance that has magnitude, for example how big or how much, but does not take into account direction is called a scalar. A quantity such as displacement that has both magnitude and direction is called a vector. Hopefully you now understand the conceptual difference between distance and displacement. Understanding concepts is half the battle in physics, the other half is math. A stumbling block to new physics students is trying to wade through the math of physics while also trying to understand the associated concepts. This struggle may lead to misconceptions and answers that make no sense. Once the concept is mastered, the math is far less confusing. So let's review and see if we can make sense of displacement in terms of numbers and equations. You can calculate an object's displacement by subtracting its original position, v sub 0, from the final position, v sub f. If the final position is the same as the initial position, then delta d equals 0. Ahora que sabemos la diferencia entre distance y displacement, conceptual y matemáticamente, podemos trabajar en el siguiente ejercicio. A cyclist rides 3 kilometers west and then turns around and rides 2 kilometers east. What is her displacement? What distance does she ride? What is the magnitude of her displacement? To solve this problem, we need to find the difference between the final position and the initial position, while taking care to note the direction on the axis. The final position is the sum of the two displacements, delta d1 and delta d2. 1. Displacement. The rider's displacement is delta d equals delta sub f minus delta sub 0, that is negative 1 kilometer. 2. Distance. The distance traveled is 3 kilometers plus 2 kilometers, that is 5 kilometers. 3. The magnitude of the displacement is 1 kilometer. Con ese ejercicio culminamos con el video de hoy. Si tienes dudas sobre el contenido o la solución del ejercicio, no dudes en dejar tus preguntas en los comentarios. Ahora les dejo con el siguiente dato curioso. Physicists make calculations all the time, but they do not always get the right answers. In 1998, NASA, the National Aeronautics and Space Administration, launched the Mars Climate Orbiter, a $125 million satellite designed to monitor the Martian atmosphere. It was supposed to orbit the planet and take readings from a safe distance. The American scientists make calculations in English units, feet, inches, pounds, etc., and forgot to convert their answers to the standard metric SI units. This was a very costly mistake. Instead of orbiting the planet as planned, the Mars Climate Orbiter ended up flying into the Martian atmosphere. The probe disintegrated. It was one of the biggest embarrassments in NASA's history.